Now it is your turn. Let's put these ideas into 3 labs. For Lab 1, you will implement Kahn's algorithm for a course catalog. Give it a try before you look at the solution. The graph has 8 courses with prerequisites. For example, CS 102 needs CS 101, and CS 301 needs both CS 201 and Math 102. First, build the adjacency list and the in-degree array from the edge list. Then run Kahn's algorithm and print the course order that comes out. Finally, check that the order has all 8 courses, so there is no cycle, and that every prerequisite comes before the course that needs it. The solution starts from the edge list. This array holds all 8 prerequisite edges as pairs of course numbers. This loop adds each edge to the adjacency list and counts the in-degree. For every edge from U to V, in-degree at index V increases by 1. Then we make an order array to hold the result. We call Kahn topo sort. It fills the order array and returns how many vertices it placed. The printed order is 0, 3, 1, 4, 6, 2, 5, 7. Every course appears after its prerequisites. The full program is in the course code folder. It compiles and runs clean under the sanitizers. An account equal to 8 confirms there is no cycle. For Lab 2, you will implement Dijkstra's algorithm with a priority queue. This is the version that pushes duplicates and skips old entries. Give it a try. The graph has 6 vertices and 9 directed edges. For example, the edge from 0 to 1 has weight 2, and the edge from 2 to 3 has weight 3. First, build the adjacency list from the edge list. Then run Dijkstra from vertex 0 and print the distance array. Finally, by hand, check at least one distance by adding the edge weights along its shortest path. The solution builds the graph with add edge calls. This first line adds 3 edges out of vertex 0 and vertex 1, each with its weight. The second line adds 3 more edges, out of vertex 1 and vertex 2. The third line adds the last 3 edges, out of vertex 3 and vertex 4. Then we make the distance array. We call Dijkstra from vertex 0, and it fills the distance array. In the output, the distance to vertex 0 is 0. That is the source, so its distance is 0. The distance to vertex 5 is 11. That is the largest distance in this graph. The full program is in the course code folder. You can check vertex 5 by hand. The path 0, 1, 2, 3, 4, 5 costs 2 plus 1 plus 3 plus 2 plus 3, which is 11. That matches the distance to vertex 5. Lab 3 is the challenge. You will implement Prim's algorithm and reuse the heap from Chapter 12 as the frontier. Give it a try. The graph has 6 vertices and 8 undirected edges. For example, the edge between 1 and 2 has weight 1, the smallest in the graph. First, build the adjacency list and add each edge in both directions, because the graph is undirected. Then run Prim from vertex 0 and print each tree edge and the total weight. Finally, compare your total against a minimum spanning tree you trace by hand. The solution builds the graph with add undirected edge calls. Each call adds the edge in both directions at once. This first line adds the edges touching vertex 0. The second line adds the edges from vertex 1 to vertices 2 and 3. The third line adds the edge from 2 to 3 and the edge from 3 to 4. The fourth line adds the last 2 edges up to the edge between 4 and 5. Then we make the parent array and the key array. We call Prim from vertex 0. It fills the parent array, which records how each vertex joined the tree. In the output, the first tree edge is 2 to 1, with weight 1 the cheapest edge. The total minimum spanning tree weight is 11. The full program is in the course code folder. The printout lists one edge per vertex in vertex index order taken from the parent array. That is not the order the edges were declared, nor the order the vertices join the tree. That completes the 3 labs and the chapter on graph algorithms. Nice work. You can now trace and code the course shortest path and spanning tree algorithms.